Hi, this is Baird Givens, and in this video, I'm going to introduce you to something called the Union Lemma and then explain why it's true. Okay? So the Union Lemma says, let's say that I have a set X. Actually, let's say a set A. A is a set. And this set has this special property. For all little c in capital A, there is a set U sub c such that little c is an element of U sub c, and U sub c is a subset of capital A. So let's draw a diagram. So this is still just the hypothesis. I haven't said the conclusion yet, but let's draw a diagram. So the diagram would be, I have this set A, consists of everything inside that little shape. And every point that I take in A, so if I take any C in A, I can find another set which contains C, but is a subset of A. Okay, contains C, but is a subset of A. And I can do this at every point. So at every point, there's some set that contains each one of these points. Okay. Then the union over C and A of U sub C. So what does this mean? This means I'm going to take a union of all of these sets that I've drawn, all these little different colored sets. I'm going to union all of them, and I'm going to union them all for every single point C and A. So I'm going to get a point, like for every point, there's going to be a set around it. And so the U sub C's are all of these, and I get one for every single point of A. So the C in A underneath means I'm getting one for every single point. So what do I get when I take this union? What will this union equal? And I claim that it equals capital A. Okay? So let's prove this. How do we prove that two sets are equal? There's two sets here on this, this equality that I'm trying to prove. This equality has two sets. So I'm trying to prove this right here. I'm trying to prove a set on one side, which is a union, is equal to a set on the other side, which we just call A. So the method of proving that two sets are equal is to do a subset style proof. So you take an element on one side, you show it's on the other side, and then vice versa. Okay? So let's prove this. Proof. All right. Let's do this direction first. So let's let little d be an element over the unions of all the C's in A of U sub C's. So that means that D is in at least one of the U sub C's. By the definition of this union, the definition of this union is that D is in U sub C for some C in A. Okay. So I have the picture that I had before I drew a million things all over it. Here's my A. Here's my C. Here's U sub C. And D is somewhere in there. D is somewhere inside there. Okay. What do I know about U sub C? I know two things. I know, first of all, that C is in it, and then I also know that it's a subset of A. Also, U sub C is a subset of A. So by definition of subset, since D is on the left-hand side of this, and the left-hand side is a subset of A, therefore, D is in A. Okay? So we started by showing that D was in the left-hand side of this equality, and then we showed that it's in the right-hand side of this equality. All right, now we're going to do the other direction. So now we'll start with D being an element of capital A. So that means that D is equal to one of these C's, okay? D is equal to one of these C's. So by hypothesis, D is in U sub D, which is one of the sets whose union is being formed. So D, since it's in one of these sets, that means that it's in the whole union, because you only have to be in one of the sets to be in the union. So let's go back up to the picture and talk through what both of these parts mean in the picture. So the first part was basically saying that when I union all of these sets, I stay inside of the set A. So intuitively, why would that be true? That as I take the union of all of these sets, I never do like this, okay? I never go outside of A. Why is that? Well, because of the hypothesis, we have this hypothesis over here that says that each one of them is contained in A. So the first part of the proof is basically saying, well, since they're all inside of A, then even after I union them together, it's still all inside of A, okay? And then the second part of the proof is saying that every D in A gets covered by one of these circles. So every D in A gets covered by one of these circles. So like there's not going to be like some D, maybe there's a D right here that got missed, right? From what I drew so far, that got missed. But the idea is that, well, you just keep drawing more and more of these. So even if it looks like temporarily, like there's one that's missed, you're going to just draw more U's. And so since every single point gets covered by a U, nothing gets left out. Okay, nothing gets missed. And so that's essentially what the two parts of the proof are saying. The first part is saying that all of these little circles stay inside of my set A. And then the second part is saying that every point of A gets covered by one of them. All right, so that's the union lemma. It ends up being very important in topology and in some other classes. So thank you for listening.